Hello everyone, and welcome back to another Physics Friday. And today we're going to be looking at one of my favorite things, I think, from mechanics, and that is the springdulum. So it is kind of really exactly what it sounds like. It's a spring pendulum. So you take a pendulum, and instead of making, the arm rigid, you make it a spring, so it's bouncing up and down, and you get some nice stuff with something with resonance. I'll link the Steve Mold video down below. It's really cool. But anyways, what we end up getting is, a springdulum. In this video, we're just going to be deriving the equations of motions for it. And we're going to be using some Lagrangian mechanics. But before we get started, I do want to just define a couple of things. First and foremost, we're just going to be defining the length of our springdulum as r, and the displacement from the central axis, angular displacement from the central axis. We're going to be calling that theta. So this is really just a sort of polar coordinates, nothing too special, really. So yeah, let's actually get calculating some Lagrangian things. And when I say Lagrangian things, I really just mean our Lagrangian. I cannot draw today. Right. So Lagrangian is just going to be equal to our kinetic energy, of course, minus our potential energy. So let's think about what our kinetic energy is going to be first. So we know that our kinetic energy is just 1/2 m times v squared, but we do have 2 degrees of freedom here. It can move, up and down like this, because it's a spring, but it can also move side to side. It has this full plane of motion to move in. And because of that, we can't just define our velocity squared as just some sort of scalar value. It really needs to be a vector. And because of that, we're just going to use the fact that, or define this, I suppose. We just know that v is equal to r dot times r hat in polar coordinates plus r times theta hat. Or sorry, r times r dot times theta hat, where the dots just represent time derivatives. And this right here is just our generalized velocity in polar coordinates, nothing too special. So the way we're going to find t then, or our kinetic energy, is really just use the fact that this is m over 2, and then, well, that is not a 2, my gosh. This is m over 2, and then v dot v. And this right here is just going to be equal to m over 2, and then this dotted with itself. Take the dot product and you square each of the components. So we're going to have r dot squared plus r theta dot squared. And yeah, that's really just our kinetic energy. And now on to the potential energy. So we're going to have 2 types here. We're going to have our gravitational potential energy, but also we're going to have our kinetic energy. Or not kinetic energy, elastic potential energy, goodness me, it's been a day. So our gravitational potential energy, it really isn't that bad actually. So we're just going to say this right here is quote-unquote ground, so that's where this is h equals 0. It's kind of the point we're comparing it to. So we're going to say mg times h naught, but that's just 0, minus mgh. And what we're left with really is just our gravitational potential energy is just equal to minus mgh. You might be a bit concerned that there's a minus sign there, but don't worry about it. It is supposed to be there. It's throwing me off a bit, but don't worry about it. It's all good. And our second type of potential energy is going to be our elastic potential energy, which is really just quite simply k over 2 times r squared, and it's r squared simply because that's the length of our actual spring here. So using these 2 things right here, what we have as so this is our t right here. We have our v, which is going to be negative mgh plus 1/2 kr squared. We can simplify this a tiny bit more, because you'll notice we have an h here, and no h is anywhere else. So let's just kind of take a look at this right here. You'll notice that if we just kind of draw a parallel line here, that this distance right here, this vertical distance right here, that's just our h. So really just using properties or some basic trigonometry, we know that h is just equal to r times the sine of theta, r times the cosine of theta. Meaning that we can just express our potential energy as minus mgh, minus mgr times the cosine of theta plus 1/2 kr squared. So now that we have our potential and kinetic energy, what we can do is just subtract the two and find our Lagrangian. So we know then that our Lagrangian, right over here, is just equal to m over 2 times r dot squared plus r theta dot squared minus, but that minus becomes a plus actually, plus mg r cos theta minus 1/2 k r squared. And although this isn't pretty, what we're going to do with it isn't all too bad. So what we're going to do here is use the Euler-Lagrange equation real quick, which I shall write out. So the Euler-Lagrange equation simply states that the partial derivative of our Lagrangian with respect to our first function, because you'll notice here that we have two functions. We have some r of t, and we also have some theta of t. And based off this, we can define basically where our springdulum is at any point in time. So we can say that like f1, for example, is just r of t, and then theta of t is say like f2. The notation just fi is just for the generalization of it. But please don't be confused. Minus the derivative with respect to time of the partial derivative of our Lagrangian with respect to f prime, or fi prime. And this must be equal to 0 at all times. So that is kind of a mouthful and a bit confusing perhaps with the notation, but let's just kind of break it down, and you'll see it really isn't all too bad. So let's just start with differentiating with respect to r. So what we're going to have is the partial derivative of our Lagrangian with respect to r minus the derivative with respect to t of the partial derivative of our of our Lagrangian. Of our Lagrangian. And that must be equal to 0, but I'm just going to set these equal to each other because I'm lazy. And using this, we just have to differentiate this with respect to r. If it's not an r, then we don't really care about it, and it's a constant. So using this, we end up finding that, well, that first term r dot squared, well, that we're differentiating with respect to r, taking the partial derivative, that is, so we don't care about r dot. What we have is just m times r, but then theta dot squared. And that just comes from the fact that we bring the 2 down, just basic power rule stuff, really. And then we're just going to add mg times the cos theta, because that's just all that's a constant relative to r. And then we're just going to have minus kr here. And that must be equal to the derivative with respect to time of the partial derivative with respect to r dot of our Lagrangian. And that right there is actually a lot simpler because we only have one place where that appears. So that's just the derivative with respect to time of m times r dot, which is really just equal to m times r double dot. And you'll see that this has like a resemblance to almost like Newtonian, like F equals ma, and there was a reason for that. We'll get back to it. So this is like one equation. But let's move on to the other, and we can find it for our second equation for theta. So what we have here then for our angle is just going to be, I'll draw a little line right here actually. What we have here, actually I'm going to, just real quick, housekeeping, I'm just going to move this to the side real quick, don't mind me. Boop. So that way we can kind of focus on what we're doing. So I'll move this down. Alright. That way you can still kind of see it. So we're going to do the same thing, but just for theta now. So the partial derivative with respect to theta of all of this, well, every term goes to 0 except for this middle one right here. So what we have is just minus mg times r sine of theta. That's the theta. Which is equal to, yeah, that's right, okay. Which is equal to the, sorry, I just want to make sure that's right. Which is equal to the time derivative, which is just equal to the derivative with respect to time of the same thing, but we're differentiating now with respect to theta dot. Meaning that we just have an m times r squared theta dot. And I'm not going to expand this a little bit right here, just because it does get really ugly, and product rule is not fun sometimes. So yes. So in short, these really are our equations of motion for our springdulum. If you just, well, if you really just kind of erase, if you just really erase this bit right here, and say this is equal to mr dot dot. These are the equations. This is a system of differential equations for our springdulum. And you might be saying, well, that looks incredibly ugly, and they really aren't the nicest things to look at, but they do reduce really nicely. So say we say, because they should reduce to a normal spring and normal pendulum whenever we plug in the right things, right? So if we say, all right, k is equal to 0, basically meaning that, well, we're not moving up or down at all. And if you say theta is also equal to 0, so this is literally just like, or sorry, not theta equals 0. If you say k is 0, this is just, we should just get the normal pendulum back, right? So if we take a look at this equation right here on the top, and we say, okay, well, if k is 0, well, nothing changes. But one thing we also have to note is that if k is 0, then r is actually just constant, meaning that if k is 0, and we're assuming this is just like, you know, r is constant, then we end up just getting that m theta dot dot is equal to minus mg over r times sine of theta. Those are the m's cancel, and this is just your equation for a normal pendulum. And then if you do something similar on the bottom, where you say, all right, well, let's just make the stationary, like, you know, not change theta at all. So say, all right, so theta is equal to 0, basically meaning that theta prime, or sorry, theta dot is 0. What you end up getting is mg, well, times 1, cosine 0 is 1, minus kr is equal to mr dot dot, which is just the exact same thing as if we were to do a normal spring hanging up and down. With gravity, of course. So yeah, this is really just the equations of motions for a springdulum. I hope you all enjoyed this small little video about Lagrangian mechanics, and I hope to see you all in the next Physics Friday. Thank you for watching. Adios.